Let's continue from the session 6 continuation of algebra of limits. So the last operation that is left over is division. So that is limit n tending to infinity xn by yn is equal to L by m. This is where the denominator is a positive quantity, that is m is a non-zero quantity. So we need to prove this. So let's start this proof. So from this we will be able to tell that limit n tending to infinity 1 by yn is equal to 1 by m. This is for m non-zero, that is m is a positive quantity. And what do we know? Since yn is a convergent sequence which tends to the limit m, which is a non-zero quantity, therefore there exists m1, let me choose m1 belonging to n, such that modulus of yn minus m is less than m by 2. This is for all n greater than m1. This is for all n greater than m1. So now by choosing this, let me choose the values in such a way that minus modulus of m by 2 is less than modulus of yn minus modulus of m is less than modulus of m by 2. Let me choose the positive quantity like this. Since it's less than by 2, I am choosing all. Since we proved this in the previous theorem, if it is convergent, then its modulus is also a convergent sequence, so we are able to write it like this. Now adding modulus plus m throughout for this, what I am going to get is, again this is for all n greater than m1. So here it will be what? Modulus of m minus modulus of m by 2 is less than modulus of yn is less than modulus of m by 2 plus modulus of m. This is again for all n greater than m1. So we get modulus of m by 2 is less than modulus of yn, and here it will be 3 modulus of m by 2. This is for all n greater than m1. So we were able to write it like this. Now here let me take the reciprocals for this, reciprocal of this quantity. If I consider 1 by modulus of yn, here it is greater than, since we are taking reciprocal, it will be less than 2 by modulus of m. This is for all n greater than m1. Okay, we are able to arrive at this stage. Now let me consider there exists m2 belonging to another quantity m2 in n, such that modulus of yn minus m is less than what we consider m square epsilon by 2. This is for all n greater than m2. We choose this quantity. We are choosing this quantity m square epsilon by 2. Where we know epsilon is a positive quantity, is any real number. Now let capital M be the max of m1 and m2. Maximum of m1 and m2 you are considering capital M. Okay, now 1 by modulus of yn is less than 2 by modulus of m, and the other quantity is modulus of yn minus m is less than m square epsilon by 2. This is for all n greater than m, since we are choosing m is the max of m1 and m2. So now let me consider 1 by yn minus 1 by m is equal to what? When I cross multiply this, I get m minus yn by m dot yn. So this is equal to what? Modulus of m minus yn into modulus of 1 by yn into modulus of 1 by modulus m minus yn into modulus of 1 by yn into modulus of 1 by m. But we know the quantity for this. That is, what is modulus of m minus yn? That is, yn minus m is m square epsilon by 2. So it is less than m square epsilon by 2. Since it's a positive quantity, whether it's yn minus or m minus yn, the value is m square epsilon by 2. Into what is 1 by modulus of yn? That is 2 by modulus of m. Into 1 by modulus of m. This is for all n greater than m. Right? So this is for all n greater than m. So what do we get now? Finally here it's going to get cancelled. See here, we are going to see m square, modulus of m, positive quantity, m square, 2. So it is just less than epsilon. So we get modulus of 1 by yn minus 1 by m is less than epsilon. This is for all n greater than m. Therefore, limit n tending to infinity 1 by yn is equal to what? 1 by m from this condition. This is where m is a positive quantity. And what do we know? Limit n tending to infinity xn by yn will be limit n tending to infinity xn into limit n tending to infinity into 1 by yn. We know the limit xn is L dot, and we have just now proved it is 1 by m, and therefore it is L by m, where m is a non-zero quantity, and hence we have proved this. You need to note one more thing, that is the converse of this statement given in the above theorem is not true. For example, see, that is illustrated with an example. That is, if two convergent sequences, if the xn and yn are two convergent sequence, whether it is addition, subtraction, multiplication and division, holds good. It is also a convergent. But the converse, the other side is not true. If the addition of two convergent, like for example, if I take xn plus yn, this is a convergent sequence, okay? Sequence. Then the sequence individually xn and yn need not be convergent. Need not be convergent. Okay. So let us illustrate with an example. For example, xn is minus 1 to the power of n. I will consider xn. Yn is minus 1 to the power of n plus 1. But what will be xn plus yn? Will be minus 1 to the power of n plus minus 1 to the power of n plus 1. So the answer is gets cancelled, and here the answer I am going to get is 0, which converges to 0. So this convergent sequence, which is converging to sequence, 0 sequence. But what do I know? xn is an oscillatory sequence, yn is an oscillatory sequence, but the final answer I am getting, it is a convergent sequence. So this can be convergent individually, it need not be convergent.